Assalamualaikum and salam sejahtera. Today lecture is the topic for today lecture is bipolar junction transistor or BJTs. Okay, this is the introduction to BJT. Okay, what is the learning outcome from this lecture? At the end of this chapter, students able to identify and explain the construction, characteristic, operation, and configuration. Okay, now let us look at the BJT construction. It has 3 alternately doped semiconductor and 2 PN junction. There are 2 types of transistor, PNP and NPN. The terminals are labeled as E is stand for emitter, B is for base, and C is the collector. Okay, as you can see in this figure here. Okay, this is the terminal, base, emitter, and also collector. The symbol for the transistor, electrical symbol for the transistor is at the right side of this figure. C stands for collector, B is the base, and E is the emitter. If you look at the direction of current, arrow current here, if the current is moving from emitter to base, this transistor is called PNP transistor. But if the current move from base to emitter, so this transistor is called NPN transistor. Okay, so the arrow in the graphic symbols define the direction of current here. So now we look at the BJT operation. With the external sources VEE and VCC connected as shown below, the emitter base junction is forward bias and the base collector junction is reverse bias. So here, as you can see in this figure, the direction of current here is moving from emitter and to the base over here, and also to the collector junction over here. So it depends on the connection of the source. Okay, the connection of the source can change. That is, this is the positive polarity and this is the negative polarity, same as this one. If you change the direction of the polarity, so the current, it will be moved like this. Okay, the difference is that if you the configuration is like this, what will happen, the transistor is actually a PNP transistor, since the current is moving this direction. But if you change the configuration, for example, this is plus and this is minus, this is plus and this is minus, so the current will be flowing this direction, and the type of transistor will change, that is NPN. Alright. Okay, before I move on to the next slide, for NPN, the base current will move upward. Okay, so current IC will move in this direction, opposite direction from this figure, and current IE will move opposite direction from this figure, so it will move like this if we change the polarity of the source, and the configuration here will become NPN. Alright, now we go on to the next slide. This is the BJT biasing. So as you can see here, there are three types of configuration. So the first one is the cutoff region, the second one is the saturation region, and the third one is active region. So what is cutoff region? When BE junction, BE stands for base emitter junction, and CB is stand for collector base junction, are reverse bias. Therefore, large depletion layer will there will be large depletion layer at the junction here. Okay. Only extremely small amount of reverse current flowing from E to C. Okay, so here only small amount of current that will flow because of the large depletion layer. This is what we call as depletion layer. So this depletion layer will become large, like one is over here and the other section is over here. So when it becomes large, only extremely small amount of reverse current flowing from emitter to collector. The second one is about saturation region. Further increases the IB, not cause IC also increase. So that is the saturation region. Saturated is when IC is at maximum possible. It is opposite the cutoff region. Okay, we will look at this condition when we reach the operating region over here. I will explain much more detail when we add this slide. So the third condition is active region, proper biasing arrangement. So this is the condition when BE junction, CB junction, and also operating region. So this is what will happen, the condition. Okay, now we go on to the BJT current. Emitter current is the sum of the collector and base current. So as you can see here, by looking at the figure here, you can see that IE is the summation of IC plus IB. This is the configuration for NPN transistor. Okay, so IC mostly in milliamp. The unit for collector current is usually in milliamp, and the unit for IB, base current, usually in microampere. So the assumption that we can make is that IE is approximately IC and VBE is equal to 0.7 volt. Usually VBE is 0.7 volt. It depends on the configuration. If you use other configuration, VBE might be changed. Okay, the collector current is comprised of two current. IC is equal to IC majority and ICO minority. O stands for the leakage current. So this is the configuration for PNP transistor. Okay, the current will move from emitter to the collector and also the base. And the symbol here, the current will move from emitter to base compared to the NPN from base to emitter. So please make sure that you know the symbol, because sometimes student can make mistake because they don't understand the symbol of transistor, and this will cause the equation will be different. So transistor characteristic, a terminal of the BJT as common reference. There are three types of configuration, as you can see here: common base CB, common emitter CE, and common collector. So now we look at the first configuration. The first one is common base configuration. You can see from the figure here. So the arrow in the graphic symbol defines the direction of emitter current conventional flow through the device. So the notation and symbol used in configuration with the transistor in the majority of text and manual for the common base configuration with PNP and NPN. This is the configuration for common base. The base is usually the terminal closest to or at ground potential. So mostly common base configuration, the ground at the base terminal. The base terminal. The base is common to both input emitter base IE and VBE output collector base of the transistor IC and VCB. If you look here, I have explained before at the previous slide, when the polarity of source, this is plus and this is minus, what will happen? This is forward bias, so the current IE will move in this direction. Okay. This configuration is PNP. So here will become reverse bias. If you change the polarity of your source like this is plus and this is minus, plus and minus, what will happen? The current will be flowing this direction. So this is actually reverse bias, and this is actually forward bias, but the current is moving in this direction. Right. So now we go on to the next slide. Operating region of common base. So this is the output or collector characteristic for a common base transistor amplifier, and this is the input or driving point characteristic for a common base silicon transistor amplifier. I just want to show you about this. Okay, the VBE value here equals to 0.7 volt because it uses silicon. Okay, if you change this into germanium, this will be 0.3 volt. Alright, okay, back to the slide for operating region. So this graph demonstrates the output current IC to an input voltage VCB for various level of input current IE. So this is the operating range of the amplifier. Okay, this is for IE equals to 1 ampere, IE equals to 0 milliampere. Sorry, this is 1 milliampere. This is IE equals to 2. So this is actually the active region. The unshaded area here is the active region. The gray area over here is the saturation region, and this is the cutoff region. So this is the operating range of the amplifier. Amplifier will on at this range. Amplifier is basically off at this cutoff region. There is voltage but little current, while in saturation region the amplifier is full on. There is current but little voltage over here. So the graph is actually IC versus VCB. So because this is the common base configuration, so this is the output or collector characteristic for a common base transistor amplifier. Alright, in the active region, the base emitter junction is forward bias, whereas the collector base junction is reverse bias in this common base characteristic. Okay, so the common base current, emitter and collector current approximately IC is approximately IE. All this formula you need to take note, because you guys need to remember all this formula. We will use this formula for the DC and AC analysis of BJT. So please take note all this formula and write it down. Okay, base emitter voltage VBE equals to 0.7 volt. Alpha here relates the DC current IC and IE. This is the formula for alpha DC. In the DC mode, the level of IC and IE due to the majority carriers are related by a quantity called alpha. So this is alpha DC, and defined by the following equation. So this is the equation where alpha DC equals to IC over IE. Ideally, alpha is equals to 1 because IC is approximately to IE. But in reality, alpha is between 0.9 and 0.998. So alpha in AC mode, this one alpha in DC, and now this is alpha in AC mode. So alpha AC equals to delta IC over delta IE. Delta means difference, difference of point in IC divided by difference of point in IE. So we go on to the next slide. Okay, now we go on to the common emitter configuration. As you can see here, for common emitter configuration, the emitter is grounded. So